Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches between stars, where ancient visitors carry stories from worlds we will never see. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the darkness beyond Neptune's orbit, two objects drift through space with velocities that betray their alien origins. They move too fast for captivity by our sun's gravity, their trajectories carved by forces that began in stellar nurseries dozens of light years away. When the universe was hundreds of millions of years younger, and the galaxy's spiral arms held different configurations of dust and gas. One tumbles end over end, a reddish shard perhaps 400 meters long, its surface weathered by cosmic rays and micrometeorite impacts accumulated over millions of years in the interstellar medium. The slow bombardment of high-energy particles has gradually altered its surface chemistry, converting simple organic molecules into complex polymers that absorb blue light and reflect the deeper wavelengths, painting it the color of rust or dried blood. The other trails a gossamer tail of sublimating ice, glowing faintly in the distant sunlight like a celestial brushstroke painted across the void. As solar radiation heats its surface, buried volatile compounds, water ice, carbon monoxide, nitrogen transition directly from solid to gas, carrying with them microscopic dust grains that catch and scatter photons in a process unchanged since comets first formed in the outer regions of stellar disks. The tail points away from the sun, shaped by radiation pressure and the solar wind into a structure that extends for millions of kilometers, visible only because space telescopes can detect the faint fluorescence of excited molecules against the cosmic background. Both are visitors from the galactic deep, messengers from star systems that formed when our own solar system was still a swirling disk of dust and possibility. Their journey through interstellar space has exposed them to conditions unlike anything experienced by objects that remained gravitationally bound to their parent stars. The interstellar medium, though nearly empty by terrestrial standards, contains enough hydrogen atoms, helium nuclei, and dust particles to gradually erode surfaces and alter chemical compositions over geological timescales. Magnetic fields threading through the galaxy accelerate charged particles to energies that can penetrate deep into solid matter, creating new isotopes and breaking molecular bonds in a slow process of cosmic weathering. The first carries the designation Oumuamua, named for the Hawaiian word meaning scout or messenger from afar arriving first. The name itself whispers of humanity's ancient relationship with the sky, chosen by astronomers who understood they were witnessing something unprecedented in the recorded history of our species. For thousands of years, humans have watched comets appear and disappear, tracking their predictable returns, weaving them into mythology and calendar keeping. But Oumuamua represents something fundamentally different, a visitor that belongs to no solar orbit, a fragment of deep space that happened to intersect our gravitational neighborhood for a brief moment before continuing its billion-year journey across the galaxy. The second bears the more technical label 2I Borisov, later redesignated as 3I Atlas, after more careful orbital analysis revealed subtle perturbations in its path that required additional observations to resolve. The renaming reflects the challenge of tracking objects that move against the stellar background at unprecedented speeds, requiring new algorithms and observational strategies developed specifically for interstellar visitors. Their names reflect humanity's growing awareness that we inhabit not an isolated system, but a way station in the galaxy's vast migration of matter, a temporary harbour for objects whose journeys began before Earth's continents took their current shapes, before complex life emerged from the primordial oceans. These objects share a fundamental strangeness that sets them apart from every asteroid and comet catalogued in our solar system's family portrait. They move through space on hyperbolic orbits, open curves that will carry them back into interstellar darkness after their brief passage through our neighbourhood. Mathematical analysis of their trajectories reveals orbital eccentricities greater than 1, meaning their paths through space describe not ellipses but hyperbole curves that approach, but never close upon themselves. Their velocities exceed the sun's escape speed by margins that cannot be explained by gravitational perturbations from the known planets, marking them as permanent exiles from whatever stellar systems gave them birth. The physics of their motion speaks to violent histories. Objects achieve interstellar velocities only through catastrophic gravitational encounters, close approaches to massive planets during the chaotic early epochs of stellar system formation, or tidal disruption events when binary stars pass near developing planetary systems. Computer simulations suggest that every star system ejects vast quantities of solid material during its formation phase, launching asteroid-sized objects into interstellar space at velocities ranging from a few kilometers per second to tens of kilometers per second. The galaxy thus becomes filled with debris from countless episodes of planetary formation, a vast ocean of wandering fragments that occasionally intersect the gravitational sphere of influence of other stellar systems. Yet their differences hint at the diversity hidden in the cosmic deep, the vast population of wanderers that drift unseen through our galaxy's spiral arms. One shows no visible activity, its surface darkened by eons of radiation exposure, a process that gradually converts organic compounds into complex carbon chains that absorb sunlight across the visible spectrum. The darkening occurs because cosmic rays break apart methane, ammonia, and other simple molecules, creating free radicals that recombine into larger structures resembling asphalt or charcoal. This process, known as space weathering, operates continuously on any surface exposed to the interstellar radiation field, gradually reducing reflectivity and reddening color over timescales measured in millions of years. Astronomers measure its color as unusually red, similar to objects in the outer reaches of our own solar system that have been cooked by cosmic radiation for billions of years. The Kuiper belt objects and long-period comets show similar spectral signatures, suggesting common processes of surface alteration that operate wherever ice and organic compounds meet high-energy radiation. Yet subtle differences in the absorption features hint at compositional variations, different ratios of carbon to oxygen, varying abundances of nitrogen-bearing compounds, trace elements that reflect the unique chemistry of the stellar nursery where formation occurred. The other behaves like the comets we know, shedding material as it approaches the sun's warmth, its coma and tail revealing familiar molecules, water vapor, carbon monoxide, dust grains that catch and scatter light in patterns that speak of ice sublimating into vacuum. Spectroscopic observations detect the characteristic emission lines of hydroxyl radicals, the photodissociation products of water molecules broken apart by solar ultraviolet radiation. The coma expands symmetrically around the nucleus, creating a roughly spherical cloud of gas and dust that extends for hundreds of thousands of kilometers, visible in telescopic images as a fuzzy patch that obscures the central object. Both challenge our understanding of what wanders between the stars, and both arrived at a moment when human technology could finally recognize them for what they are. Only in the past few decades have our telescopes become sensitive enough to detect such small, dark objects racing through the outer solar system at unprecedented speeds. The challenge lies not merely in their faintness, though they reflect only a tiny fraction of the sunlight that illuminates them, but in their rapid motion against the stellar background. Traditional asteroid surveys search for objects that move slowly across the sky, following predictable paths that can be extrapolated from a few nights of observation. Interstellar visitors move too quickly for such leisurely analysis, requiring immediate follow-up observations before they fade beyond the reach of ground-based telescopes. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, and the Catalina Sky Survey represent humanity's first systematic attempt to monitor the sky for exactly these kinds of visitors. Their CCD cameras sweep the heavens night after night, comparing new images with archived observations, searching for points of light that move too fast and in the wrong directions. The automated detection algorithms flag objects whose motion vectors indicate hyperbolic orbits, triggering alerts that mobilize observational resources around the world. This represents a new kind of astronomy time domain surveys that monitor the entire visible sky for transient phenomena, capturing events that would have been missed entirely by previous generations of astronomers. The universe has been sending us these gifts for billions of years. Only now we have learned to see them. Statistical models derived from the detection rates of Oumuamua and subsequent visitors suggest that several interstellar objects pass through our solar system every year, most too small or too distant to detect with current instruments. The calculations paint a picture of constant traffic through the outer solar system, a steady stream of wandering fragments that approach from random directions, follow hyperbolic trajectories round the sun, and disappear back into the cosmic deep without leaving any trace of their passage, except for the gravitational perturbations they impart to dust particles and the occasional asteroid. We live in a cosmic shooting gallery, bombarded constantly by debris from stellar formation processes that occurred when the galaxy was young. Every cubic parsec of interstellar space likely contains thousands of these wandering fragments, the scattered remains of planetary systems that formed, evolved, and were torn apart by the gravitational dance of binary stars or the violent death throes of their parent suns. The density of interstellar objects probably varies with location in the galaxy, higher near star-forming regions where planetary systems are currently ejecting material, lower in the voids between spiral arms where only the oldest wanderers survive their million-year journeys through near-empty space. The recognition of this hidden population transforms our understanding of galactic ecology. Stars do not evolve in isolation but participate in a vast exchange of matter that connects stellar systems across hundreds of light-years. Gravitational interactions during the early epochs of planetary system formation launch solid material into interstellar space at velocities sufficient to reach neighboring star systems within a few million years. This process, known as lithopanspermia, could theoretically transport not only minerals and organic compounds, but also microbial life between worlds, seeding the galaxy with the chemical precursors of biology, or even living organisms capable of surviving the harsh conditions of interstellar space. Computer simulations of stellar system formation reveal the violent dynamics that create these wandering populations. During the first few million years after a protoplanetary disk begins to condense into solid bodies, gravitational interactions between embryonic planets scatter vast quantities of smaller objects onto trajectories that carry them beyond the gravitational reach of their parent star. The process resembles a cosmic pinball machine, with developing planets acting as gravitational slingshots that accelerate debris to escape velocity. Objects that approach too closely to massive worlds receive gravitational kicks that can double or triple their orbital velocities, transforming stable members of a planetary system into permanent exiles. The same mechanisms operate in reverse when these wanderers encounter other stellar systems during their galactic wanderings. Occasionally, an interstellar object passes close enough to a massive planet to lose energy through gravitational interaction, trading velocity for a more tightly bound orbit that transforms the visitor into a permanent resident. Jupiter's gravitational influence dominates such capture processes in our solar system, though the probability remains extremely low. Most interstellar visitors pass through the outer solar system without coming close enough to any planet to significantly alter their trajectories, continuing their journeys with only minor perturbations from the Sun's gravity well. Theoretical studies suggest that captured interstellar objects might be hiding in plain sight among the irregular satellites of the giant planets, or in co-orbital resonances with Jupiter and Saturn. These objects would be indistinguishable from native solar system bodies after billions of years of orbital evolution. Their interstellar origins erased by the gradual effects of planetary perturbations and tidal forces. Some of the Trojan asteroids that share Jupiter's orbit might be ancient interstellar captures, their unusual compositions and orbital properties preserving subtle clues about their foreign origins. The outer satellites of the giant planets, with their distant, highly inclined orbits, represent another possible hiding place for objects that entered our solar system from interstellar space during its early history. Yet the vast majority of interstellar visitors remain unbound to our gravitational system, following open trajectories that carry them back into the galactic deep after their brief encounter with solar warmth. Like planetary archaeologists examining ancient artifacts, we measure their light and calculate their paths, extracting stories written in spectral lines and orbital mechanics. Each visitor carries chemical signatures from distant worlds, frozen samples of stellar evolution, compressed narratives of galactic history encoded in the ratios of isotopes and the presence of trace elements that formed in the nuclear furnaces of alien suns. Spectroscopic analysis reveals the fingerprints of familiar molecules: water ice, carbon monoxide, nitrogen, silicate minerals, the basic building blocks of rocky worlds and icy bodies that apparently form around other stars through processes similar to those that shaped our own solar system. These measurements provide our first direct sampling of matter from beyond our solar system, allowing us to test theories about planet formation and stellar evolution against actual physical evidence, rather than relying entirely on theoretical models and observations of distant protoplanetary disks. The chemical composition of interstellar visitors also constrains models of galactic chemical evolution. Different stellar populations produce different ratios of heavy elements through nucleosynthesis, creating gradients in metallicity that vary with distance from the galactic center and with stellar age. Interstellar objects preserve records of the chemical conditions that existed in their birth environments, potentially allowing astronomers to trace their origins back to specific regions of the galaxy or even specific types of stellar systems. Isotopic ratios of carbon, nitrogen, and oxygen could reveal whether an object formed in the disk of a metal-rich star or in the outer regions of a metal-poor system, while the presence of unusual isotopes might indicate formation near a supernova or in the outflow from an evolved giant star. they drift past our cameras and spectrographs in a matter of months. Their brief appearances measured in observing sessions and telescope time allocation committees. Ground-based observatories coordinate worldwide campaigns to track these objects as they race toward perihelion and then fade into the cosmic background. Their angular velocities often exceeding the tracking limits of large telescopes designed to follow slowly moving targets. Space-based telescopes like Hubble and Spitzer contribute their unique capabilities, imaging the visitors in wavelengths invisible to human eyes, searching for clues about their composition and internal structure that cannot be obtained from ground-based observations. Each observation becomes precious, irreplaceable data that will never be duplicated, for these objects follow one-way trajectories that carry them beyond the reach of our most powerful instruments. The observational campaigns require careful coordination between multiple facilities, with astronomers racing against time to gather as much information as possible before the visitors disappear forever. Priority targets receive round-the-clock monitoring, with telescopes in different hemispheres handing off observations as Earth's rotation carries each facility out of view. The data streams from these campaigns photometric measurements, spectroscopic observations, astrometric positions represent humanity's only direct encounter with matter from other stellar systems. The urgency of these observations has revolutionized certain aspects of astronomical practice. Traditional scheduling processes, with their months-long proposal review cycles, cannot accommodate targets that remain visible for only a few weeks. Instead, observatories have developed rapid response capabilities that allow high-priority observations to be scheduled within hours of target identification. This new mode of operation bridges the gap between planetary science and stellar astronomy, requiring instruments designed for solar system observations to be quickly reconfigured for studies of interstellar visitors that behave unlike any previously catalogued objects. Then they disappear forever into the darkness from which they came, their brief interaction with our star's gravity well completed, their orbital energy unchanged by the encounter, except for the tiny momentum transfer associated with radiation pressure and the emission of thermal photons. They continue their journeys across the galaxy at speeds measured in kilometers per second, carrying with them whatever secrets they acquired during their formation in alien stellar nurseries billions of years ago. In 1,000,000 years, they will be light years away, still tumbling through the void, still preserving their cargo of ancient ice and primordial rock, still bearing witness to the processes that shaped worlds we will never visit. The vastness of their future trajectories dwarfs human comprehension, distances so large that light itself, travelling at the ultimate speed limit of the universe, requires years to cross the gaps between their current positions and their eventual destinations. Yet these objects maintain their structural integrity across such spans of time and space, their surfaces slowly evolving under the constant bombardment of cosmic radiation, while their interiors remain frozen in the conditions that existed when they first condensed from the cooling debris of stellar formation. The physics of their survival speaks to the remarkable stability of solid matter in the near vacuum of interstellar space. Unlike objects orbiting close to active stars, interstellar wanderers experience minimal heating and virtually no atmospheric drag or tidal forces that could disrupt their structure. The primary agents of change operate on geological timescales. Cosmic ray bombardment gradually alters surface chemistry. Micrometeorite impacts create new crater fields and expose fresh material, and the slow sublimation of volatile compounds reshapes topography over millions of years. These processes proceed so slowly that objects launched from stellar systems during the galaxy's youth could still preserve recognizable traces of their original composition today. Temperature measurements of interstellar objects reveal the profound cold that characterizes their environment. Far from any stellar heat source, their surfaces equilibrate with the cosmic microwave background radiation at temperatures near 3 degrees above absolute zero. At such temperatures, most chemical reactions proceed infinitely slowly, and even quantum tunneling effects that normally facilitate molecular transformations become negligible. Water ice becomes harder than steel, nitrogen freezes solid, and organic compounds enter a state of chemical suspended animation that could preserve complex molecules for billions of years. This natural refrigeration creates time capsules that sample the chemical conditions existing in stellar nurseries when the galaxy was young. The recognition that these objects exist transforms our understanding of the solar system from an isolated island to a harbour in the galactic ocean. We are not alone in our corner of the Milky Way, but connected through the constant traffic of interstellar matter to every star system in our neighbourhood. The same gravitational processes that ejected these visitors from their birth systems continue to operate today, launching new wanderers into the cosmic deep while capturing others in temporary gravitational embraces. Our own solar system contributes to this galactic diaspora, ejecting comets from the Oort cloud through interactions with passing stars and scattering asteroid fragments through close encounters with Jupiter and the other giant planets. Statistical analyses suggest that our solar system has probably launched millions of objects into interstellar space during its 4 billion year history. The most massive ejection events likely occurred during the late heavy bombardment, when migrating giant planets gravitationally scattered vast populations of asteroids and comets throughout the solar system. Some fraction of this debris received sufficient energy to escape the Sun's gravitational influence entirely, carrying samples of Earth's neighbourhood into the broader galaxy. These objects now wander between the stars alongside visitors from thousands of other stellar systems, participants in a slow but constant exchange of solid material that connects star formation regions across hundreds of light years. The isotopic signatures preserved in meteorites provide evidence for this ancient trafficking of matter between stellar systems. Certain meteorites contain mineral grains that predate the formation of our solar system, their isotopic compositions matching the predicted outputs of specific types of stellar nuclear synthesis. These presolar grains survived the violent processes that destroyed and reformed most of the solid material in the early solar nebula, preserving direct samples of matter that condensed in the atmospheres of ancient red giant stars or in the expanding shock waves of supernovae. Their presence demonstrates that interstellar space contains a vast reservoir of solid material launched from countless stellar systems during their formation and evolution phases. Similar processes likely operate throughout the galaxy, creating vast populations of wandering objects that carry chemical information between star systems. The metallicity gradients observed in stellar populations suggest that this mixing process has operated throughout galactic history, gradually homogenizing the chemical composition of the interstellar medium while preserving local variations that reflect recent episodes of star formation and stellar death. Interstellar visitors represent mobile agents in this chemical evolution, transporting heavy elements synthesized in the nuclear cores of massive stars to regions of the galaxy where new generations of planets can incorporate these materials into their formation processes. Yet the detection of only 2 confirmed interstellar visitors in human history highlights the challenge of studying this population. The objects remain invisible until they pass close enough to the Sun for terrestrial telescopes to detect their reflected light, and even then they appear as point sources indistinguishable from asteroids except for their unusual orbital characteristics. Their small sizes and dark surfaces make them difficult targets for spectroscopic analysis, requiring the largest ground-based telescopes operating at their sensitivity limits to obtain even basic compositional information. Most interstellar objects probably pass through the outer solar system undetected, their brief appearance against the stellar background falling between the observational cadence of automated sky surveys. The development of more sensitive detection systems promises to revolutionize our understanding of the interstellar object population. The upcoming Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, will monitor the entire southern sky every few nights with unprecedented depth and temporal resolution. Computer models predict that this survey could detect dozens of interstellar visitors each year, providing the statistical sample sizes necessary to characterize the population as a whole, rather than relying on the unique properties of individual objects. Space-based infrared telescopes could detect the thermal emission from interstellar objects too dark to observe in visible light, extending the detection range to smaller and more distant targets. Future interstellar visitors might even become targets for robotic space missions, though the technical challenges remain formidable. The high velocities of hyperbolic objects require massive energy expenditures to achieve rendezvous trajectories, while their unpredictable arrival times make it difficult to prepare missions in advance. Conceptual studies have explored the possibility of high-velocity flyby missions that could return close-up images and compositional measurements without attempting to match orbital velocities. Such missions would require new propulsion technologies and spacecraft designs optimized for brief encounters at relative speeds measured in tens of kilometers per second. The brief passage of each interstellar visitor through our detection zone represents a unique opportunity to sample matter from distant stellar systems without the expense and complexity of interstellar travel. These objects serve as natural space probes, carrying physical samples across distances that dwarf the scale of human space exploration and delivering them to convenient locations within our own solar system. Their chemical and isotopic compositions provide ground truth for theories about planet formation, stellar nucleosynthesis, and galactic chemical evolution that would otherwise remain forever beyond the reach of direct experimental verification. This realization brings with it a kind of cosmic loneliness. We are part of something much larger than ourselves, yet forever separated by distances that dwarf human comprehension. The interstellar visitors connect us to the broader galaxy, while simultaneously emphasizing our isolation. They carry news from stellar systems that will never appear as more than points of light in our most powerful telescopes, samples from worlds whose surfaces we will never map, chemical signatures from processes that occurred when the universe was young. Their silent passage through our neighborhood serves as a reminder that we inhabit a small oasis of warmth and complexity in an ocean of dark, cold emptiness populated by wandering fragments of ancient worlds. The first recognition came quietly, without fanfare, embedded in the routine data streams of an automated sky survey operating from a mountaintop in Hawaii. On October 19, 2017, the Panoramic Survey Telescope and Rapid Response System detected a faint point of light moving against the stellar background at an angular velocity that immediately flagged it as unusual. The object appeared unremarkable in initial observations, a dim speck reflecting sunlight like thousands of other small bodies that populate the outer solar system. Yet its trajectory told a different story, one that would force astronomers to confront the reality that our solar system receives regular visits from fragments of alien worlds. Robert Varick, the astronomer who first noticed the anomalous motion, recalls the moment of realization when preliminary orbital calculations revealed an eccentricity greater than 1. Such values indicate hyperbolic trajectories, open curves that approach the Sun from interstellar space and then depart forever, rather than the closed ellipses that characterize objects gravitationally bound to our stellar system. The mathematics contained an unmistakable signature. This object originated beyond the gravitational influence of the Sun, arriving from the direction of the constellation Lyra after a journey that likely lasted millions of years through the cosmic void. The discovery triggered a worldwide observational campaign as astronomers raced to characterize the visitor before it faded beyond the reach of ground-based telescopes. Major observatories around the globe redirected their instruments toward the rapidly moving target, coordinating observations across multiple wavelengths and time zones to maximize the scientific return from this unprecedented opportunity. The urgency stemmed from the object's trajectory. It was already past its closest approach to the Sun and accelerating back toward interstellar space, its apparent brightness decreasing daily as it receded into the outer solar system. Initial spectroscopic observations revealed a surface composition that defied easy categorization. The object reflected light with a distinctly reddish color, similar to some asteroids in the outer solar system that have been darkened by eons of cosmic radiation. Yet it showed no signs of cometary activity, no coma of sublimating ice, no tail streaming away from the solar wind. Its spectrum lacked the characteristic absorption features of water ice or hydrated minerals that astronomers expected to find on an object that had survived a multi-million-year journey through the interstellar medium. Instead, the reflected light suggested a surface covered in organic compounds that had been gradually polymerized by high-energy radiation into complex carbon chains. The object's rotation presented another puzzle. Photometric observations revealed brightness variations that repeated every 34 hours, indicating that the visitor tumbled end over end as it traveled through space. The amplitude of these variations, the difference between maximum and minimum brightness, suggested an extremely elongated shape, perhaps 10 times longer than it was wide. Computer models attempting to match the observed light curve required aspect ratios that pushed the boundaries of structural stability for solid objects, leading to speculation about whether the visitor might be a fragment of a larger body that had been tidally disrupted during a close encounter with a massive planet or stellar companion. The International Astronomical Union faced the unprecedented challenge of naming humanity's first confirmed interstellar visitor. Traditional nomenclature for asteroids and comets assumes objects that belong to our solar system, following predictable orbits that can be catalogued and referenced indefinitely. But this object would disappear forever after its brief passage, never to return to the inner solar system. The naming committee ultimately chose Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first, acknowledging both the observatory that discovered it and the profound significance of its interstellar origin. As observational data accumulated, the object's unusual properties deepened rather than resolved the mysteries surrounding its nature and origin. High-resolution imaging attempts with the Hubble Space Telescope failed to reveal any extended structure or surface features, confirming that the visitor was indeed very small, probably no more than a few hundred meters in its longest dimension. Its lack of detectable cometary activity puzzled astronomers who expected any icy object to show signs of sublimation when heated by solar radiation, especially one that had spent millions of years in the near absolute zero environment of interstellar space. Thermal infrared observations provided additional constraints on the object's properties. The visitor absorbed solar energy during its passage through the inner solar system and re-radiated that energy at longer wavelengths characteristic of its surface temperature. The balance between absorbed and emitted radiation allowed astronomers to estimate the object's size and albedo, the fraction of incident sunlight that it reflected rather than absorbed. These measurements confirmed that Oumuamua was both small and dark, reflecting only about 10% of the sunlight that illuminated its surface, similar to the darkest asteroids in our own solar system. The trajectory analysis revealed subtle but significant deviations from a purely gravitational orbit. As Oumuamua receded from the Sun, it accelerated slightly faster than Newton's laws predicted, as if some additional force was acting to increase its velocity. The magnitude of this non-gravitational acceleration was tiny, about 1 part in 10,000 of the Sun's gravitational pull at the object's position, but it was statistically significant and persistent across multiple observations. Similar accelerations characterize active comets, where the rocket effect of sublimating ice provides a small but measurable thrust that modifies orbital trajectories over time. Yet Oumuamua showed no visible signs of the gas and dust emission that typically accompanies cometary outgassing. Sensitive observations with ground-based telescopes and the Spitzer Space Telescope searched for the characteristic signatures of water vapor, carbon monoxide, and dust particles that should have been detectable if the visitor was shedding material at rates sufficient to explain its anomalous acceleration. The non-detections placed upper limits on outgassing rates that were orders of magnitude lower than those observed from active comets at similar distances from the Sun. This contradiction between the object's cometary-like acceleration and its asteroid-like appearance sparked intense debate about the visitor's true nature. Some astronomers proposed that Oumuamua was predominantly rocky, like an asteroid, but contained small deposits of volatile material in subsurface pockets that could sublime without creating a detectable coma. Others suggested that the object might be composed of unusual materials, perhaps nitrogen ice that would sublime at lower temperatures than water, or organic compounds that could outgaze without producing the spectroscopic signatures typically associated with cometary activity. The mystery deepened when theoretical studies examined the probability of detecting such an object. Statistical models based on stellar formation rates and planetary system evolution predicted that interstellar visitors should be relatively rare, with only a few objects passing through the inner solar system each century. The discovery of Oumuamua so soon after systematic sky surveys achieved the sensitivity necessary to detect such objects seemed remarkably fortunate, or perhaps indicative of a much larger population of interstellar wanderers than theoretical models predicted. As Oumuamua faded beyond the detection limits of even the most powerful telescopes, it left behind more questions than answers. Its brief passage through our solar system had confirmed that interstellar objects exist and occasionally visit our neighborhood, but its unusual properties defied easy categorization within the traditional framework of asteroid and comet science. The visitor challenged assumptions about the nature of small bodies in interstellar space, the efficiency of various detection methods, and the frequency with which alien material intersects our gravitational domain. The mystery of Oumuamua's strange accelerations lingered in the scientific literature like an unsolved riddle, spawning dozens of theoretical papers that attempted to explain how an apparently inert object could exhibit the dynamical behavior typically associated with active comets. The non-gravitational forces acting on the visitor were real and measurable, detected independently by multiple observational teams using different telescopes and analysis techniques. Yet the physical mechanism responsible for these forces remained elusive, hidden beneath the object's dark, unreflective surface, and obscured by the vast distance that separated it from Earth-based instruments. Traditional explanations for non-gravitational accelerations in the solar system invoke the rocket effect of sublimating volatiles water ice, carbon monoxide, nitrogen, and other compounds that transition directly from solid to gas when heated by solar radiation. The escaping gas streams carry momentum away from the object's surface, creating a small but persistent thrust that can significantly alter orbital trajectories over time. Comets routinely exhibit such behavior, their spectacular tails serving as visible evidence of the mass loss that drives their non-gravitational motions. Yet Oumuamua showed no signs of the gas and dust emission that should accompany significant outgassing, creating a paradox that challenged conventional understanding of small body physics. Some astronomers propose that the visitor might be shedding material composed of molecules too small or too dispersed to detect with existing observational techniques. Hydrogen gas, for instance, would be virtually invisible to most spectroscopic surveys, but could still provide sufficient thrust to explain the observed accelerations if produced in large enough quantities. The photodissociation of water ice could generate hydrogen through a multi-step process. Solar ultraviolet radiation breaks apart water molecules into hydrogen and oxygen atoms, and the light hydrogen atoms escape into space, while the heavier oxygen remains bound to the surface. This mechanism could operate even when traditional cometary activity remains below detection thresholds. Alternative theories explored more exotic possibilities. Perhaps Oumuamua was not a conventional rocky or icy body, but rather a fragment of unusual composition that could outgaze without producing detectable emissions. Nitrogen ice, for example, sublimates at lower temperatures than water and produces gas that lacks strong spectroscopic features in the wavelength ranges, typically monitored by astronomical surveys. If the visitor originated in a stellar system with different chemical abundances than our own, it might be composed of materials that behave in unexpected ways when exposed to solar heating. The most speculative explanations ventured into uncharted theoretical territory. Some researchers suggested that Oumuamua might be an artificial object, a piece of alien technology that happened to pass through our solar system during its multi-million-year journey between the stars. The object's unusual shape, its lack of detectable outgassing, and its anomalous acceleration could all be explained if it were constructed rather than naturally formed. While such scenarios remained highly speculative and unsupported by direct evidence, they highlighted the degree to which the visitor's properties challenged conventional explanations. Radiation pressure offered another potential mechanism for the observed accelerations. Sunlight carries momentum as well as energy, and when photons are absorbed or reflected by a solid surface, they transfer that momentum to the object. For small bodies with low densities and high surface area to mass ratios, radiation pressure can provide measurable accelerations that modify orbital trajectories. Computer models suggested that Oumuamua might have an extremely low density, perhaps comparable to aerogel or another highly porous material that would make it susceptible to radiation pressure effects large enough to explain its non-gravitational motion. The thermal recoil effect, known as the Yarkovsky effect, could also contribute to the observed accelerations. Objects in space absorb solar energy during their daytime periods and re-radiate that energy as thermal infrared photons during their nighttime periods. If the object rotates slowly enough, the peak thermal emission occurs when the warmest surface faces away from the sun, creating a net thrust in the direction of orbital motion. For Oumuamua, which rotated every 7.34 hours and had an elongated shape that would create strong thermal gradients across its surface. The Yarkovsky effect could potentially produce accelerations of the right magnitude to match observations. yet each proposed explanation carried its own set of assumptions and limitations. The hydrogen outgassing model required that Oumuamua be composed almost entirely of water ice, despite spectroscopic observations that suggested a rocky or carbonaceous composition. The nitrogen ice hypothesis demanded formation conditions unlike those found in our own solar system, implying that the visitor originated in a stellar environment with fundamentally different chemistry. The artificial object scenario, while intriguing, remained scientifically unprovable, given the available observational data and the vast distances involved. The radiation pressure explanations required the object to have structural properties that pushed the boundaries of physical plausibility, for radiation pressure to account for the observed accelerations. Oumuamua would need to be extremely lightweight, perhaps less dense than cork or balsa wood, while maintaining structural integrity sufficient to survive millions of years in interstellar space and the thermal stresses associated with its close passage by the Sun. Such characteristics seemed inconsistent with the dark, apparently solid surface revealed by photometric observations. As observational opportunities dwindled and Oumuamua faded into the cosmic background, astronomers were forced to accept that many fundamental questions about the visitor would remain permanently unanswered. The object's true composition, internal structure, and formation history would forever remain matters of speculation rather than empirical determination. Its brief passage through our detection zone had provided tantalizing glimpses of its properties, but insufficient data to construct a complete physical model that could explain all of its unusual characteristics. The scientific legacy of Oumuamua extends beyond the specific puzzles it presented to the broader recognition that interstellar objects represent a new class of targets for observational astronomy. The visitor demonstrated that space contains populations of small bodies with properties that may differ significantly from those of objects that have remained gravitationally bound to stellar systems throughout their histories. The harsh conditions of interstellar space, extreme cold, persistent radiation, and isolation from stellar heat sources could produce surface modifications and internal structures unlike anything found among familiar asteroids and comets. Future detections of similar objects would be necessary to determine whether Oumuamua represented a typical example of interstellar wanderers or an unusual outlier whose properties reflected unique formation conditions or evolutionary processes. The visitor's anomalous characteristics might be common features of objects that have survived multi-million-year journeys through the cosmic void, or they might result from rare circumstances that would not be repeated in subsequent discoveries. Only through the statistical analysis of multiple interstellar visitors could astronomers hope to distinguish between universal properties of the population and idiosyncratic features of individual objects. The technological and observational challenges revealed by Oumuamua's discovery also highlighted the need for new approaches to studying transient astronomical phenomena. Traditional observational strategies, designed for objects that remain visible for months or years, proved inadequate for targets that race through the inner solar system in a matter of weeks. The rapid pace of hyperbolic trajectories demanded immediate follow-up observations, coordinated international campaigns, and flexible scheduling procedures that could accommodate high-priority targets with minimal advance notice. The second arrival emerged from deep space like an answer to unspoken questions, its trajectory first detected by amateur astronomer Gennady Borisov using a modest 0.65-meter telescope at the Margot Observatory in Crimea. On August 30, 2019, Borisov noticed a fuzzy patch of light moving against the stellar background at a rate that suggested either a very distant comet or something far more extraordinary. His initial observations captured an object displaying the characteristic coma and tail of an active comet, but preliminary orbital calculations hinted at velocities that exceeded the Sun's escape speed within days. Follow-up observations from professional observatories around the world confirmed what Borisov had suspected. Humanity had detected its second confirmed visitor from interstellar space. Unlike the enigmatic Oumuamua, this new visitor behaved exactly as astronomers expected an interstellar comet to behave. As it approached the Sun along its hyperbolic trajectory, solar heating sublimated volatile compounds from its surface, creating an expanding coma of gas and dust that glowed faintly in reflected sunlight. The spectroscopic signatures were immediately familiar water vapor, carbon monoxide, hydrogen cyanide, and other molecules common in solar system comets. Here was an object that seemed to bridge the gap between the familiar and the alien, displaying recognizable cometary activity while carrying the unmistakable dynamical signature of an interstellar origin. The International Astronomical Union designated the visitor as 2I Borisov, acknowledging both its status as the second confirmed interstellar object and its discoverer's contribution to this historic detection. Later refinements to its orbital trajectory led to a redesignation as 3I Atlas, reflecting more precise calculations that incorporated additional observational data from professional surveys. The nomenclature changes highlighted the evolving understanding of the object's properties as more sophisticated analysis techniques were applied to the growing dataset of positional measurements and spectroscopic observations. Detailed observations revealed a visitor that seemed refreshingly normal in its abnormality. The nucleus, estimated to be roughly 1 to 2 kilometers in diameter, was significantly larger than Oumuamua, but still small enough to be classified as a minor body by solar system standards. Its coma extended for tens of thousands of kilometers around the central nucleus, fed by the steady sublimation of surface ices exposed to increasing solar radiation. The tail, pointing away from the Sun and shaped by radiation pressure and the solar wind, stretched for millions of kilometers behind the nucleus, creating a ghostly brushstroke visible in wide-field telescopic images. Spectroscopic analysis provided the first detailed chemical fingerprint of matter from another stellar system. The abundances of water, carbon monoxide, and other volatile compounds fell within the ranges observed for solar system comets, suggesting that the basic chemistry of planet formation operates similarly around other stars. The ratio of carbon monoxide to water vapor was somewhat higher than typical for comets from our own Oort cloud, but not dramatically so well within the range of variations observed among different families of solar system objects. The discovery of familiar molecules in an alien visitor provided powerful confirmation that the laws of chemistry and physics operate consistently throughout the galaxy. The same processes that condensed water ice and carbon compounds in the outer regions of our own protoplanetary disk apparently operated with similar efficiency in the stellar nursery where 2I Borisov formed billions of years ago. This chemical similarity suggested that the basic ingredients for life water, carbon compounds, nitrogen-bearing molecules might be common features of planetary systems throughout the galaxy, increasing the probability that biological processes could emerge wherever conditions permit liquid water to exist. Yet subtle differences in the visitor's composition hinted at the diversity that might characterize interstellar populations. The elevated carbon monoxide abundance could reflect formation at greater distances from its parent star, where temperatures remained low enough for this volatile compound to condense directly from the gas phase. Alternatively, it might indicate different chemical conditions in the original protoplanetary disk, perhaps variations in the carbon-to-oxygen ratio, or the presence of organic compounds that could decompose to produce carbon monoxide when heated by solar radiation. The object's activity level remained remarkably constant as it approached perihelion, suggesting a relatively homogeneous composition and structure, unlike some solar system comets that experience dramatic outbursts or exhibit seasonal variations in their outgassing rates. 2I Borisov maintained steady activity levels that varied smoothly with its distance from the Sun. This consistency allowed astronomers to make reliable predictions about its future behavior and plan observational campaigns that could maximize the scientific return from its brief passage through the inner solar system. Thermal modeling of the nucleus provided estimates of its size, albedo, and rotation properties. The visitor appeared to be a dark object, reflecting only about 4% of the incident sunlight, comparable to some of the darkest asteroids in our own solar system, and consistent with the surface composition dominated by organic compounds that had been processed by cosmic radiation during its interstellar journey. Its rotation period derived from variations in the brightness of the coma as different portions of the nucleus became exposed to solar heating, was estimated at roughly 25 hours, a relatively slow spin that suggested the object had not been significantly disrupted by tidal forces or collisional processes during its formation or subsequent evolution. The nucleus exhibited a slightly elongated shape, though far less extreme than the cigar-like proportions inferred for Oumuamua. Computer models of the light variations suggested an aspect ratio of perhaps 2, 1, or 3:1, well within the range observed for solar system comets and consistent with the gravitational reshaping that occurs during the collapse of weakly bound rubble pile structures. This relatively normal geometry provided additional evidence that 2I Borisov represented a fairly typical example of the small bodies that form in the outer regions of planetary systems around other stars. High-resolution imaging attempts with the Hubble Space Telescope succeeded in resolving the visitor's coma and detecting structure within the dust envelope that surrounded the nucleus. The images revealed asymmetries in the brightness distribution that suggested preferential outgassing from specific regions of the nuclear surface, possibly indicating compositional heterogeneities or topographical features that focus sublimation activity. These observations provided the most detailed views ever obtained of matter actively sublimating from an interstellar object, offering insights into the physical processes that govern cometary activity in objects that have spent millions of years in the extreme cold of interstellar space. The dust particles ejected from the nucleus carried information about the solid materials that condensed in the visitor's birth environment. Polarimetric observations, which measure the preferential orientation of light waves reflected from microscopic particles, suggested that the dust grains were similar in size and composition to those found in solar system comets. The particles appeared to be composed primarily of silicate minerals mixed with organic compounds, creating a dark, fluffy material that efficiently scattered sunlight while absorbing most of the incident energy. As 2I Borisov approached its closest point to the Sun in December 2019, its activity level increased in response to the growing intensity of solar heating. The coma expanded to encompass hundreds of thousands of cubic kilometers, while the tail stretched across tens of millions of kilometers of space. Yet throughout this period of peak activity, the visitor maintained the steady, predictable behavior that had characterized its approach phase, never exhibiting the dramatic outbursts or fragmentations that sometimes occur when solar system comets venture close to the Sun for the first time. This new visitor displayed expected comet behavior with a visible tail, yet carried its own mysteries that emerged slowly through careful observation and analysis. As 2I Borisov continued its journey toward perihelion, astronomers noticed subtle anomalies that distinguished it from the solar system comets with which they were familiar. The visitor's outgassing patterns, while generally predictable, showed minor variations that suggested internal structural complexities or compositional heterogeneities not immediately apparent from its external appearance. The nucleus seemed to rotate in a way that exposed different surface regions to solar heating at regular intervals, creating periodic fluctuations in activity levels that painted a picture of an object with distinct geological provinces. Detailed spectroscopic monitoring revealed that the relative abundances of different gas species varied slightly as the comet progressed along its orbit. Water vapor dominated the composition near perihelion, as expected from theoretical models of ice sublimation, but the ratios of carbon monoxide to water and hydrogen cyanide to water showed subtle temporal variations that hinted at stratified layers within the nucleus. These changes suggested that the visitor's interior was not uniformly mixed, but rather composed of discrete regions with different volatile inventories, perhaps reflecting variations in the temperature and chemical conditions that existed during its original formation. The dust production rate, measured through photometric observations of the coma's brightness and extent, followed patterns that were both familiar and strange, like solar system comets. 2I Borisov exhibited increased activity as it approached the Sun and decreased activity as it receded, following the expected relationship between solar heating and ice sublimation rates. Yet the specific functional form of this relationship differed slightly from empirical models derived from observations of native comets, suggesting either differences in thermal properties or variations in the depth distribution of volatile materials within the nucleus. Polarimetric measurements of the scattered light from dust particles in the coma provided additional clues about the visitor's physical properties. The degree of polarization varied with wavelength in patterns that revealed information about the size distribution, shape, and composition of the microscopic grains ejected from the nuclear surface. These particles appeared to be remarkably similar to dust from solar system comets, fluffy aggregates of silicate minerals and organic compounds with sizes ranging from nanometers to micrometers. Yet subtle differences in the polarization curves suggested minor variations in the grain properties that could reflect different formation environments or processing histories. Radio observations detected the thermal emission from the nucleus itself, providing direct measurements of its surface temperature and thermal inertia. The visitor's surface warmed and cooled in response to solar heating cycles in ways that were generally consistent with expectations for a low-density, highly porous object similar to solar system comet nuclei. Yet the thermal response showed minor deviations from standard models that suggested either variations in surface properties across the nucleus or internal heat sources that contributed to the overall energy budget. These anomalies were subtle detectable only through careful comparison with theoretical predictions, but they hinted at physical processes that might distinguish interstellar objects from their solar system counterparts. The search for unusual isotopic ratios in the visitor's outgassed volatiles represented one of the most ambitious attempts to characterize matter from another stellar system. Different stellar environments produce different isotopic signatures through variations in nucleosynthesis processes, stellar mass loss rates, and chemical mixing efficiencies. The ratio of deuterium to hydrogen in water molecules, for instance, depends on the temperature and density conditions that existed during the collapse of the original molecular cloud from which the visitor's parent stellar system formed. Similarly, the abundance of heavy nitrogen isotopes reflects the degree of chemical processing that occurred in the protoplanetary disk before solid bodies began to condense. High-resolution spectroscopic observations with ground-based telescopes and space-based instruments pushed the limits of current technology in attempts to detect these isotopic signatures. The measurements required extremely precise wavelength calibration and sophisticated modeling of atmospheric absorption, features that could contaminate the weak spectral lines associated with isotopic variants of common molecules. Most isotopic ratios remain below the detection thresholds of existing instruments, but upper limits on deuterium enhancement in water vapor suggested values consistent with formation in environments similar to our own solar system. The non-detection of exotic isotopic signatures provided important constraints on theories about the visitor's origin and evolution. The absence of dramatic deuterium enhancements argued against formation in extremely cold environments where isotopic fractionation processes could operate with unusual efficiency. Similarly, the lack of unusual nitrogen isotope ratios suggested that the visitor formed in a stellar system with metallicity and chemical evolution patterns similar to those characterizing our own galactic neighborhood. These null results were scientifically valuable, ruling out formation scenarios involving exotic stellar environments or unusual chemical processing mechanisms. Attempts to detect organic compounds more complex than the simple molecules easily observable in gas phase spectra met with limited success. The sublimation process that creates cometary coma tends to break apart larger organic molecules, reducing complex polymers and biological precursors to their constituent atoms and simple compounds. Yet sensitive searches for specific molecular signatures, amino acid precursors, aromatic compounds, prebiotic molecules provided upper limits on their abundances that could be compared with theoretical predictions about organic chemistry in interstellar environments. The visitor's dust tail became a target for in situ sampling attempts using spacecraft already positioned in the inner solar system. While no dedicated missions were designed to intercept 2I Borisov, several operational spacecraft were repositioned to collect potential dust particles in their particle detection instruments. The European Space Agency's Bepi-Colombo mission, en route to Mercury, adjusted its trajectory slightly to increase the probability of encountering dust grains ejected from the visitor's nucleus. These particles, traveling at velocities of tens of kilometers per second relative to the spacecraft, would vaporize upon impact with detector surfaces, allowing their composition to be analyzed through mass spectrometry techniques. The results of these dust collection efforts remained ambiguous. While several spacecraft recorded impact events during the predicted encounter windows, distinguishing 2I Borisov particles from the background flux of interplanetary dust particles proved extremely challenging. The visitor's dust grains were expected to have specific chemical signatures that would mark them as interstellar in origin, but the violent impact processes that vaporized the particles for analysis also destroyed much of the isotopic and molecular information that might have confirmed their extraterrestrial nature. Ground-based radar observations attempted to probe the visitor's internal structure through direct radio reflection from the nuclear surface. These measurements, similar to techniques used to study near-Earth asteroids, could reveal information about bulk density, internal voids, and structural heterogeneities that would remain invisible to optical observations. The radar experiments required enormous technical sophistication, involving the transmission of precisely timed radio pulses toward a target moving at dozens of kilometers per second, while simultaneously receiving the extremely weak reflected signals that return to Earth several minutes later. The radar results suggested a nuclear structure that was generally consistent with expectations for a loosely bound rubble pile. Similar to many solar system comets, The bulk density appeared to be quite low, perhaps half that of water ice, indicating a highly porous internal structure with significant void space between constituent particles. This porosity could reflect the gentle accretion processes that assembled the visitor from smaller building blocks in its original protoplanetary environment, or it could result from structural modifications that occurred during its subsequent evolution in interstellar space. Yet within this generally familiar picture, the radar observations detected hints of internal complexity that distinguished 2I Borisov from well-studied solar system objects. The reflection characteristics suggested possible variations in material properties at different depths within the nucleus, perhaps indicating stratified layers with different compositions or densities. These internal heterogeneities could preserve records of the environmental conditions that existed during different phases of the visitor's formation, creating a kind of geological archive that recorded the evolution of its birth stellar system. Compositional whispers emerged from the spectroscopic analysis, like distant voices speaking a familiar language with a subtle accent. The water vapor and carbon compounds that sublimated from 2I Borisov's warming surface carried chemical signatures that echoed the molecular inventory of our own solar system, while preserving faint traces of their alien origins. Astronomers dissected the visitor's outgassed atmosphere with instruments capable of detecting isotopic ratios and molecular abundances at the parts per million level, searching for the subtle chemical fingerprints that would reveal where and how this wandering world had formed billions of years earlier in the depths of interstellar space around a distant star. The DH ratio in water molecules, the abundance of deuterium relative to ordinary hydrogen, provided one of the most sensitive probes of formation environment conditions. In our own solar system, this ratio varies systematically with heliocentric distance, reflecting the temperature gradients that existed in the early solar nebula when ice first began to condense from the cooling gas phase. Objects that formed closer to the proto-sun exhibit lower deuterium abundances, while those that condensed in the frigid outer regions show enhanced heavy hydrogen concentrations that preserve the isotopic signatures of the original interstellar molecular cloud from which our stellar system emerged. Preliminary measurements of 2I Borisov's water suggested deuterium abundances within the range observed for Oort cloud comets. Those ancient wanderers that formed in the outer reaches of our own planetary system and were subsequently scattered into distant orbits by gravitational interactions with the migrating giant planets. This similarity indicated that the basic physics of ice formation, the temperature-dependent fractionation processes that preferentially incorporate heavy isotopes into solid phases, operates consistently in protoplanetary disks around different types of stars. The visitor's chemical composition thus provided evidence for universal patterns in stellar system formation that transcend the specific characteristics of individual stellar environments. Yet beneath this broad similarity lay subtle differences that hinted at the unique evolutionary history preserved within the visitor's frozen interior. The ratio of carbon monoxide to water vapor exceeded typical values observed in solar system comets by factors of several, suggesting either formation at greater distances from the central star or different carbon-oxygen abundance ratios in the original protoplanetary disk. Carbon monoxide requires extremely low temperatures to condense as solid ice, forming only in the outermost regions of planetary systems where solar heating becomes negligible. Its enhanced abundance in 2I Borisov implied an origin in the deep freeze beyond the snowline of its parent stellar system. Nitrogen-bearing compounds provided additional clues about formation environment chemistry. Hydrogen cyanide, ammonia, and molecular nitrogen exhibit complex fractionation patterns that depend on the temperature, pressure, and radiation environment existing during the initial phases of planetary system development. The relative abundances of these species, measured through high-resolution spectroscopy as they sublimated from the visitor's nucleus, painted a picture of chemical conditions that were broadly similar to those that shaped our own solar system, yet distinct in ways that reflected the specific characteristics of an alien stellar environment. The organic compound inventory revealed through gas phase spectroscopy represented only the tip of a much larger iceberg of complex chemistry preserved within the visitor's interior. Larger organic molecules, amino acid precursors, aromatic compounds, polymeric chains would remain locked in solid form even at the relatively warm temperatures achieved near perihelion, their presence detectable only through indirect spectroscopic signatures or future sample return missions. These materials, if they existed in significant abundances, would provide unprecedented insights into the efficiency of prebiotic chemistry in environments beyond our solar system. Dust grain analysis offered another window into the visitor's composition and formation history. The microscopic particles ejected from the sublimating nucleus carried mineralogical information that complemented the gas phase spectroscopic measurements, revealing the nature of the refractory materials that provided structural support for the volatile ices. Silicate minerals dominate the composition of interplanetary dust throughout our solar system, their crystalline structures and chemical compositions reflecting the temperature and pressure conditions that existed during their original condensation from hot stellar winds or cooling supernova ejectae. Polarimetric observations of scattered sunlight from the visitor's dust coma suggested grain properties that were remarkably similar to those characterizing solar system comet particles. The size distribution, shape characteristics, and optical properties all fell within the ranges observed for native cometary dust, indicating that the fundamental processes of grain growth and aggregation operate similarly in protoplanetary disks around different stars. Yet subtle variations in the polarization curves hinted at minor compositional differences that might reflect variations in the heavy element abundances or dust-to-gas ratios that characterized the visitor's birth environment. The search for crystalline silicate minerals in the visitor's dust provided a particularly sensitive probe of thermal processing history. These minerals form only at temperatures exceeding several hundred degrees Celsius, requiring either formation close to the central star followed by radial transport to colder regions, or localized heating events such as lightning discharges or shock waves that could temporarily raise temperatures in the outer disk regions. The detection of crystalline components would indicate that the visitor's constituent materials had experienced high-temperature processing, while their absence would suggest formation in the perpetually cold outer reaches where amorphous silicates dominate. Mass spectrometry measurements of dust particles that impacted spacecraft detectors provided direct compositional information at the atomic level. These analyses, though limited by the small sample sizes and destructive nature of hypervelocity impacts, revealed elemental abundance patterns that could be compared with solar system standards. The magnesium-silicon ratios, iron abundances, and trace element concentrations all provided clues about the stellar nucleosynthesis processes that had enriched the interstellar medium from which the visitor's parent molecular cloud originally condensed. The isotopic signatures preserved in refractory elements offered particularly valuable insights into galactic chemical evolution. Different types of stars contribute different isotopic patterns to the interstellar medium through their stellar winds and supernova explosions. Massive stars produce enhanced abundances of certain oxygen and silicon isotopes, while lower mass stars contribute different patterns through their asymptotic giant branch phase mass loss. The isotopic fingerprints detected in 2I Boreov's dust could thus constrain the stellar population that had enriched its birth environment with heavy elements. Attempts to detect pre-solar grains, microscopic crystals that predated the formation of the visitor's parent stellar system, pushed analytical techniques to their absolute limits. These ancient relics, which survive the violent processes of stellar system formation because of their refractory compositions and small sizes, preserve isotopic signatures that directly record the nuclear synthesis outputs of individual stars. Their identification requires sophisticated ion beam analysis techniques that can measure isotopic ratios in regions smaller than bacterial cells, searching for the characteristic patterns that mark grains as having formed in the atmospheres of red giant stars or in the expanding shock fronts of supernova. The chemical complexity revealed by these multifaceted observations painted a picture of an object that was simultaneously familiar and exotic. Borisov appeared to be composed of the same basic materials that characterize solar system comets: water ice, carbon compounds, silicate dust, yet it preserved subtle chemical signatures that recorded its formation in an environment with slightly different physical and chemical conditions. These differences were small but scientifically significant, providing the first direct evidence for variations in planetary system formation processes that theory had long predicted, but observation had never before confirmed. The visitor's composition also provided important constraints on models of interstellar chemistry and dust evolution. During its multi-million-year journey through the galactic medium, Borisov had been exposed to cosmic radiation, stellar winds, and trace amounts of interstellar gas that could potentially alter its surface chemistry and internal structure. The preservation of volatile compounds and the apparent absence of extensive radiation damage suggested that interstellar space provides a remarkably benign environment for the long-term storage of complex organic and inorganic materials. Orbital mathematics reveals the profound strangeness hidden within apparently simple trajectories, equations that encode stories of gravitational violence and billion-year journeys across the cosmic deep. Both Oumuamua and Borisov follow hyperbolic paths through space curves that approach our solar system from infinity, bend around the sun's gravitational well, and then recede toward infinity once again. The mathematical description of such orbits requires eccentricities greater than unity, values that place these objects forever beyond the sun's ability to capture them into the closed elliptical paths that characterize the planets, asteroids, and comets that belong permanently to our stellar family. The precision of these trajectories speaks to the fundamental orderliness that underlies apparent cosmic chaos. Despite traveling through space for millions of years without any guiding intelligence, both visitors arrived in our solar system with velocities and approach angles that can be calculated to extraordinary precision using Newton's laws of motion and gravitation. Their paths through the inner solar system follow mathematical curves that were completely predictable once astronomers obtained sufficient observational data to determine their initial conditions. This deterministic behavior emerges from the same physical principles that govern planetary motions, yet applied to objects whose origins lie beyond the gravitational reach of our star. The approach velocities of both objects, roughly 26 km per second for Oumuamua and 32 km per second for Borisov, exceed the sun's escape speed at their respective discovery distances by margins that cannot be explained through gravitational acceleration from any known solar system body. These excess velocities, known as hyperbolic excess velocities, represent the speeds at which the objects were moving through interstellar space before they entered our gravitational neighborhood. They provide direct measurements of the kinetic energy that these wanderers acquired during their violent ejection from their birth stellar systems. energy that has been conserved across vast distances and enormous spans of time. The directions from which the visitors approached carry equally significant information about their origins and evolutionary histories. Oumuamua arrived from the approximate direction of the constellation Lyra, specifically from a region of sky near the bright star Vega, yet the object's journey time from that stellar neighbourhood, roughly 600,000 years at its observed velocity, means that Vega was not in its current position when the visitor began its odyssey. The proper motions of stars, their slow drift across the celestial sphere due to their individual orbital motions around the galactic centre, must be accounted for when attempting to trace interstellar objects back to their likely points of origin. Sir Borisov approached from a different direction entirely, arriving from the constellation Cassiopeia after what appears to have been an even longer journey through interstellar space. The visitor's trajectory, when traced backward through time and corrected for the gravitational effects of passing stars and giant molecular clouds, suggests an origin in a region of the galaxy that was populated by different stellar populations when the object began its wandering. These directional differences between the two confirmed interstellar visitors hint at the vast diversity of source regions that contribute to the steady traffic of alien objects passing through our solar system. The mathematical analysis of hyperbolic orbits requires sophisticated computational techniques that account for relativistic effects, radiation pressure, and the gravitational influences of all major solar system bodies. Unlike the stable elliptical orbits of planets and comets, hyperbolic trajectories are exquisitely sensitive to small perturbations that can accumulate over time to produce significant changes in the predicted path. The non-gravitational accelerations detected in Oumuamua's motion necessitated the development of new orbital determination algorithms that could accommodate force models beyond simple point mass gravitation. These computational challenges become even more complex when attempting to model the long-term evolution of interstellar trajectories over galactic timescales. The motion of objects through interstellar space is influenced not only by the gravitational fields of individual stars but also by the collective gravitational potential of the galaxy as a whole. Giant molecular clouds, stellar associations, and the central supermassive black hole all contribute to the overall force environment that shapes the paths of wandering objects over millions of years. Monte Carlo simulations that attempt to trace potential orbital histories backward in time must therefore incorporate models of galactic structure and stellar kinematics that remain uncertain at the level of precision required for definitive source identification. The statistical properties of hyperbolic orbits provide insights into the underlying physics of interstellar object ejection and transport. The distribution of approach direction should be isotropic if the galactic population of wanderers is well mixed, with equal numbers of objects approaching from all regions of the sky. Deviations from isotropy could indicate preferential source regions, perhaps associated with nearby star-forming complexes or stellar associations that are currently undergoing the chaotic dynamical evolution that launches debris into interstellar space. The small sample size of confirmed detections makes such statistical tests premature, but future surveys that detect dozens or hundreds of interstellar visitors could reveal large-scale patterns in their arrival directions. The encounter geometries of both visitors reveal the improbable precision required for detection by terrestrial observatories. Objects following hyperbolic trajectories spend only a small fraction of their time within the inner solar system where they become bright enough for observation with ground-based telescopes. The window of detectability typically lasts only a few months, during which the visitors must be both geometrically visible from Earth and positioned favourably for spectroscopic analysis. The fact that both Oumuamua and Tui Borisov were discovered during their brief passages through this narrow observational window suggests either remarkable luck or a much larger population of similar objects than early theoretical predictions had suggested. The orbital periods of hyperbolic trajectories are infinite by definition, since these objects never return to their starting points. Yet the timescales associated with their passage through the solar system provide meaningful measures of their dynamic behaviour. Oumuamua required roughly 2 years to travel from the orbit of Jupiter to its current position beyond the orbit of Saturn, while Tui Borisov spent approximately 3 years within the region, where solar heating could drive significant cometary activity. These relatively brief interaction times highlight the transient nature of our opportunity to study interstellar visitors and the importance of rapid response capabilities for maximizing scientific return. The gravitational deflection experienced by both objects during their solar encounters slightly altered their post-encounter trajectories compared to their approach paths. This scattering effect, analogous to the gravitational slingshot maneuvers used by spacecraft mission planners, change both the speed and direction of the visitor's motion through interstellar space. For Oumuamua, the deflection was small but measurable, altering its trajectory by roughly 5 degrees and increasing its speed by about 1.5 kilometers per second. Such modifications accumulate over multiple stellar encounters during the object's galactic wanderings, gradually randomizing their motions and contributing to the isotropic distribution of approach directions. The long-term orbital evolution of interstellar objects depends critically on their encounter histories with stellar systems throughout the galaxy. Computer simulations suggest that typical wanderers experience close approaches to stars roughly once every few million years, with occasional encounters that significantly alter orbital energies and directions. Objects that pass very close to massive stars or through the outer regions of binary stellar systems can receive gravitational kicks large enough to change their galactic orbits dramatically, potentially ejecting them from the galactic disk entirely, or sending them on highly eccentric trajectories that carry them far from their original formation sites. The mathematical elegance of orbital mechanics provides a framework for understanding these complex interactions, while highlighting the fundamental unpredictability that characterizes individual object histories. While the underlying physical laws are deterministic and well understood, the chaotic nature of multi-body gravitational systems makes it impossible to predict the detailed evolutionary paths of specific objects over timescales longer than a few orbital periods. This sensitivity to initial conditions ensures that each interstellar visitor carries a unique dynamical signature that reflects its particular sequence of gravitational encounters during its journey across the galaxy. These wanderers likely formed in distant protoplanetary disks, their origins tracing back to the violent ballet of planetary system formation that plays out around young stars throughout the galaxy. The process begins in the cold depths of giant molecular clouds, where gravity slowly compresses gas and dust into dense cores that eventually collapse to form new stellar systems. As the central protostar ignites nuclear fusion, the surrounding material settles into a rotating disk of debris, a cosmic construction zone where planets will eventually emerge from the gradual accumulation of countless smaller bodies. Yet not all solid material survives this formative epoch. Gravitational interactions between embryonic planets scatter vast quantities of asteroids and comets onto trajectories that carry them beyond the reach of their parent star's gravity. The early phases of planetary system formation are characterized by spectacular dynamical chaos as massive planets migrate through their birth environments, their gravitational influences reshaping the architecture of the entire system. Computer simulations of this epoch reveal a universe far more violent than the orderly arrangement of planets we observe today. Embryonic worlds collide and merge, their impacts generating debris clouds that spread throughout the planetary region. Giant planets spiral inward toward their parent stars or migrate outward to distant orbits, their changing gravitational fields scattering smaller bodies in all directions like cosmic billiard balls, responding to moving forces they cannot resist. During these tumultuous early epochs, a significant fraction of the solid material that condenses from the protoplanetary disk gets ejected entirely from the forming stellar system. Objects that venture too close to massive planets receive gravitational kicks that accelerate them beyond escape velocity, transforming stable members of the planetary family into permanent exiles condemned to wander the galactic deep. The ejection process operates with ruthless efficiency. Theoretical models suggest that young stellar systems typically expel 10 to 100 times more mass than they retain in their final planetary configurations. This size distribution of ejected objects reflects the physics of planetesimal formation in the outer regions of protoplanetary disks. Small bodies, asteroids and comets with dimensions measured in kilometers rather than thousands of kilometers are most easily scattered to high velocities because their low masses make them susceptible to gravitational perturbations that would barely affect larger objects. This preferential ejection of small bodies explains why interstellar visitors like Oumuamua and 2I Borisov are relatively tiny compared to the planets that remain gravitationally bound to their parent systems. The galaxy fills with the discarded fragments of planetary formation, while the massive worlds that ejected them continue their stately orbits around distant suns. The compositional diversity observed among the few detected interstellar visitors hints at the wide range of formation environments that characterize different stellar systems. Objects that condense in the outer regions of protoplanetary disks, where temperatures remain perpetually below the freezing point of water, will be rich in volatile compounds, water ice, carbon monoxide, nitrogen, and organic molecules that sublime readily when exposed to stellar heating. Those that form closer to their parent stars will be predominantly rocky, composed of refractory minerals that can withstand higher temperatures without vaporizing into the surrounding gas phase. The metallicity of the parent stellar system, the abundance of elements heavier than hydrogen and helium, profoundly influences the chemistry available for planet formation. Stars that formed from gas clouds enriched by previous generations of stellar evolution have access to larger inventories of carbon, oxygen, silicon and iron, enabling the formation of terrestrial planets and complex organic chemistry. Those that condensed from more pristine material, with lower heavy element abundances, may produce planetary systems dominated by gas giant worlds with minimal rocky components. Interstellar visitors thus serve as chemical messengers that carry information about the stellar nucleosynthesis history of their birth environments. The timing of ejection relative to the evolutionary state of the parent planetary system also affects the properties of interstellar wanderers. Objects scattered during the earliest phases of system formation, when the protoplanetary disk still contains significant quantities of gas, may experience drag forces that modify their surface properties and orbital characteristics. Those ejected later, after the gas has been dissipated by stellar winds and radiation pressure, follow purely ballistic trajectories determined entirely by gravitational interactions. The survival of volatile compounds on interstellar objects depends critically on this ejection timing, since early exposure to stellar radiation could drive off surface ices that would otherwise remain preserved during the subsequent journey through interstellar space. Binary stellar systems, which comprise roughly half of all stars in the galaxy, create particularly complex dynamical environments that enhance the efficiency of object ejection. The gravitational field of a binary star system varies periodically as the two components orbit around their common center of mass, creating time-dependent perturbations that can pump energy into the orbits of surrounding planetesimals, objects that venture into the gravitational sphere of influence of binary systems, experience chaotic motion that can rapidly increase their orbital eccentricities and inclinations, eventually leading to ejection when their perihelion distances become small enough for close encounters with the stellar components. The most violent ejection events occur during the close passage of stellar systems through dense star-forming regions or stellar associations. When young stellar systems encounter the gravitational fields of neighboring stars, the external perturbations can destabilize entire populations of comets and asteroids, launching them into interstellar space at velocities that reflect the relative motion between the interacting systems. These encounters may preferentially eject objects from the outer regions of planetary systems, where the gravitational binding energy is lowest and external perturbations can most easily overcome the parent star's gravitational hold. The recent discovery of free-floating planets, massive worlds that orbit no star but instead wander through interstellar space, demonstrates that even very large objects can be ejected from their birth systems under the right circumstances. If planets with masses comparable to Jupiter can be launched into interstellar space, then the ejection of much smaller asteroidal and cometary objects must be an extremely common outcome of planetary system formation. The galaxy may contain vastly more solid material in the form of interstellar wanderers than remains gravitationally bound to stellar systems, creating a vast reservoir of planetary building blocks that drift between the stars. The preservation of structural integrity during the ejection process requires that objects possess sufficient internal cohesion to survive the tidal forces and shock heating associated with close gravitational encounters. Weakly bound rubble piles may be tidally disrupted during the close stellar passages that impart escape velocities, while more cohesive objects can survive intact and carry detailed records of their formation environments into interstellar space. This selection effect means that detected interstellar visitors may represent a biased sample of the most structurally robust objects produced by planetary system formation, rather than a representative cross-section of all ejected material. The angular momentum distribution of ejected objects depends on the specific dynamical mechanisms responsible for their acceleration to escape velocity. Objects scattered by close encounters with massive planets tend to retain modest rotation rates, while those accelerated by tidal interactions with binary stars or passing stellar systems may acquire rapid spins that could affect their subsequent evolution in interstellar space. The tumbling motion observed in both Oumuamua and 2I Borisov provides clues about the violence of their ejection events and the degree of structural modification they experienced during their departure from their birth systems. The transition from gravitationally bound solar system member to free-floating interstellar wanderer represents a fundamental change in evolutionary trajectory that affects every aspect of an object's subsequent history. Once launched beyond the gravitational reach of their parent stars, these fragments begin million-year journeys through the cosmic void, carrying with them frozen samples of the chemical and physical conditions that existed during their formation, while slowly accumulating the signatures of interstellar processing that will modify their surfaces and alter their compositions in subtle but measurable ways. Each object survived million-year journeys through the cosmic void, weathered by radiation and micrometeorite impacts that gradually transformed their surfaces while preserving their ancient interiors in a state of near-perfect chemical suspended animation. The interstellar medium, though emptier than the best laboratory vacuum achievable on Earth, contains sufficient matter to slowly erode and modify any solid surface exposed to its influence over geological timescales. Hydrogen atoms, helium nuclei, and trace amounts of heavier elements drift through space at velocities measured in hundreds of kilometers per second. Their kinetic energy sufficient to sputter atoms from crystalline lattices and implant foreign elements into surface layers through low-energy ion bombardment. The cosmic radiation environment presents an even more persistent challenge to the preservation of surface materials. High-energy protons accelerated by supernova shock waves and stellar magnetic fields penetrate deep into solid matter, breaking chemical bonds and creating cascades of secondary particles that can alter molecular structures throughout the uppermost meters of exposed surfaces. This space weathering process operates continuously over million-year timescales, gradually converting simple organic compounds into complex polymeric chains that absorb visible light and redden spectral reflectance curves in characteristic patterns that have been observed on asteroids throughout the outer solar system. The galactic magnetic field threads through interstellar space with sufficient strength to deflect charged particles and create preferential directions for cosmic ray propagation. Objects traveling through this environment experience slightly different radiation doses depending on their orientation relative to the local magnetic field direction and their trajectory through regions of varying field strength. Over the course of million-year journeys, these variations in radiation exposure could create hemispheric asymmetries in surface composition and color that would preserve records of the object's passage through different galactic environments. Micrometeorite bombardment provides another source of surface modification that operates throughout the interstellar journey. The galaxy contains vast quantities of microscopic dust grains, fragments of comets, asteroid collisions, and stellar mass loss events that drift through space at velocities sufficient to vaporize upon impact with solid surfaces. Each impact excavates a microscopic crater and deposits a thin layer of shock-melted material around the impact site, gradually modifying surface texture and composition through the accumulation of billions of tiny impact events. This sandblasting process operates much more slowly in interstellar space than in planetary systems, where dust densities are enhanced by factors of thousands, but it remains detectable over the enormous timescales associated with interstellar travel. Temperature fluctuations during the interstellar journey remain minimal compared to the thermal cycling that characterizes objects orbiting active stars. Far from any significant heat source, wandering objects equilibrate with the cosmic microwave background radiation at temperatures near 2.7 Kelvin, so cold that molecular motion virtually ceases and chemical reaction rates become negligible. This extreme cold provides natural refrigeration that preserves volatile compounds and organic molecules that would decompose rapidly at higher temperatures, creating time capsules that sample the chemical conditions existing in stellar nurseries billions of years ago. Yet even in this frigid environment, subtle thermal processes continue to operate. The radioactive decay of elements like aluminum-26 incorporated during the object's formation in stellar winds and supernova ejecta provides internal heat sources that can drive slow structural rearrangements and facilitate phase transitions in crystalline materials. Additionally, the occasional passage through warmer regions of the galaxy's stellar wind bubbles, supernova remnants, or the heated gas surrounding massive star clusters can temporarily raise surface temperatures enough to mobilize volatile compounds and alter surface chemistry, in ways that preserve records of these environmental encounters. The gravitational environment of interstellar space affects the structural evolution of weakly bound objects over extended timescales. Tidal forces from passing stars, giant molecular clouds, and the galactic gravitational field itself can slowly reshape elongated objects and potentially trigger internal mass redistributions that alter rotational properties. Objects that begin their interstellar journeys with rapid rotation may gradually spin down through energy dissipation in internal friction, while gravitational torques from asymmetric mass distributions can induce complex tumbling motions that evolve chaotically over million-year periods. Magnetic field interactions present another subtle but persistent influence on the evolution of interstellar objects. Any residual magnetization acquired during formation in the magnetized environment of a protoplanetary disk will interact with the galactic magnetic field to produce weak torques that can alter rotational dynamics over extended periods. Additionally, the motion of conducting materials through magnetic fields generates electric currents that can drive electrochemical processes and produce localized heating effects that modify surface properties in ways that depend on the object's magnetic susceptibility and electrical conductivity. The passage through different galactic environments exposes interstellar wanderers to varying physical and chemical conditions that can leave detectable signatures in their surface compositions and internal structures. Dense molecular clouds provide temporary shielding from cosmic radiation, while exposing objects to higher concentrations of neutral gas that can condense onto cold surfaces and contribute to the gradual accumulation of surface contamination. Conversely, transit through supernova remnants or stellar wind bubbles. Objects to enhance radiation fields and elevated temperatures that can drive off volatile compounds and alter crystalline structures in refractory materials. Encounters with other interstellar objects represent rare but potentially significant events that could modify the properties of individual wanderers. The collision probability remains extremely low given the vast distances between objects and the three-dimensional nature of their motion through space. But statistical considerations suggest that a small fraction of long-lived interstellar objects may experience impacts with other wandering bodies during their galactic odysseys. Such collisions could fragment large objects into multiple smaller pieces, alter rotation states, or excavate subsurface materials that would otherwise remain hidden beneath space-weathered surface layers. The preservation of isotopic signatures in interstellar objects depends on the depth to which various modification processes can penetrate beneath surface layers. Cosmic ray bombardment affects only the uppermost few meters of material, while micrometeorite impacts excavate craters that typically extend no more than thousands of grain diameters into the surface. These shallow modification zones preserve most of the original bulk composition, while creating thin altered layers that record the environmental history of the interstellar journey. Core samples from future space missions to interstellar visitors could thus provide both records of ancient stellar nuclear synthesis and chronicles of galactic environmental conditions encountered during million-year wanderings. The survival statistics for different classes of materials reveal the remarkable stability of solid matter in the interstellar environment. Refractory minerals like olivine and pyroxene show minimal alteration even after extended cosmic ray exposure, while volatile compounds confined to subsurface locations remain pristine across geological timescales. Organic molecules present a more complex picture. Simple compounds may be gradually destroyed by radiation processing, while complex polymers can actually be enhanced through radiation-induced cross-linking reactions that create new molecular structures unknown in terrestrial environments. The gradual accumulation of interstellar dust and gas onto object surfaces provides a mechanism for the continuous modification of composition throughout the galactic journey. This accretion process operates most efficiently on objects with irregular shapes and porous surfaces that can gravitationally capture and retain passing particles. Over million-year timescales, the accumulated material could create detectable surface layers that preserve chemical signatures of the interstellar medium encountered during different phases of the journey, creating stratigraphic records of galactic chemical evolution. The magnetic and electrical properties of interstellar objects may evolve in response to their passage through the galaxy's variable magnetic environment. Repeated exposure to magnetic field reversals and the charging effects associated with motion through plasma environments could gradually demagnetize initially magnetized materials while simultaneously inducing new magnetic signatures that reflect the galactic magnetic field configurations encountered during the journey. These paleomagnetic records, if preserved and eventually decoded, could provide unique insights into the structure and evolution of galactic magnetic fields over cosmic time. Detection bias reveals the hidden iceberg beneath the surface of our observations, highlighting how the handful of confirmed interstellar visitors represents only the most conspicuous members of a vast population that remains largely invisible to current astronomical surveys. The objects we've discovered possess specific combinations of size, brightness, trajectory, and timing that made them detectable by terrestrial telescopes during their brief passages through the inner solar system. Yet for every interstellar wanderer that enters our detection zone at the right time and place to be observed, dozens or hundreds more likely pass through the outer solar system unnoticed, their presence marked only by gravitational perturbations too subtle to measure and reflected light too faint to distinguish from the background noise of stellar observations. The sensitivity limits of automated sky surveys define sharp boundaries in the parameter space of detectable objects. Current wide-field telescopes can identify moving targets only if they reflect sufficient sunlight to appear brighter than roughly magnitude 22, a threshold that corresponds to objects several hundred meters in diameter, with typical asteroid-like reflectivity at distances comparable to Earth's orbit around the Sun. Smaller objects remain invisible unless they pass unusually close to Earth, while larger objects become detectable at greater distances, but represent a much rarer population given the steep size-frequency distribution that characterizes small body populations throughout the galaxy. The temporal window for detection presents an even more restrictive constraint on observational completeness. Interstellar objects spend only a small fraction of their transit time through the solar system, within the geometrical and brightness limits that make them accessible to ground-based observations. Most visitors remain too distant and faint to detect until they pass inside the orbit of Jupiter, at which point they become observable for perhaps 6 months before fading beyond the sensitivity thresholds of even the largest telescopes. This brief observational window, combined with the requirement that objects be above the horizon during nighttime hours at major observatories, reduces the effective detection probability to a small percentage of all transiting objects. Directional biases in survey coverage further limit the completeness of interstellar object catalogues. Most automated sky surveys focus on ecliptic plane regions where the majority of solar system objects are found, creating blind spots at high galactic latitudes where interstellar visitors might approach from any direction. The rapid angular motion of hyperbolic objects also challenges detection algorithms designed to identify slowly moving asteroids and comets with predictable orbital patterns. Objects that cross multiple detector pixels during typical exposure times may be rejected as cosmic ray hits or satellite trails, while those that move too slowly might be dismissed as stationary background stars. The discovery statistics paint a sobering picture of observational limitations. Both Oumuamua and 2I Borisov were detected relatively close to their perihelion passages, when solar heating had already begun to affect their surface properties and outgassing behavior. Earlier detection, when the objects were still in their pristine interstellar configurations, would have provided more accurate measurements of their original compositions and physical properties. Yet earlier detection would have required more sensitive instruments operating with wider fields of view and more sophisticated data processing algorithms capable of identifying extremely faint, rapidly moving targets against crowded stellar backgrounds. Theoretical estimates of the total interstellar object flux, derived from models of planetary system formation and galactic dynamics, predict detection rates that exceed observed values by factors of 10 to 100. This discrepancy could indicate that current theoretical models overestimate the efficiency of object ejection from stellar systems, or, alternatively, that the true interstellar population consists primarily of objects too small, too dark, or too distant to detect with existing observational capabilities. Resolving this uncertainty requires either more sensitive detection systems or direct sampling of the interstellar object population through alternative observational strategies. The size distribution of the underlying population remains poorly constrained by the detection of only 2 confirmed interstellar visitors with vastly different properties. Oumuamua's estimated size of roughly 400 meters places it near the lower limit of current detection capabilities, while 2I Borisov's diameter of 1–2 kilometers makes it easily detectable even at relatively large distances from the Sun. The absence of detected objects in the intermediate size range could reflect either statistical fluctuations in a small sample or real features of the size-frequency distribution that govern interstellar populations. Larger statistical samples will be required to distinguish between these possibilities and characterize the true demographic properties of galactic wanderers. Compositional biases may also affect the observed properties of detected interstellar visitors. Objects with higher albedos, those that reflect larger fractions of incident sunlight, become detectable at greater distances and remain observable for longer periods than dark, low reflectivity targets. Similarly, objects with significant volatile inventories may become preferentially detectable when solar heating drives cometary activity that enhances their apparent brightness through light scattering from expanding dust comae. These selection effects could skew observed samples toward objects with properties that make them easier to detect, rather than those that accurately represent the broader population. The orbital inclination distribution of interstellar objects provides another dimension along which detection biases operate. Visitors that approach the solar system along trajectories roughly aligned with the ecliptic plane remain visible from ground-based observatories for longer periods than those with highly inclined orbits that carry them rapidly through northern and southern sky regions. This geometric selection effect could create apparent clustering in the orbital elements of detected objects that reflects observational limitations rather than real dynamical patterns in the underlying population. Seasonal and geographical biases in ground-based observations further complicate attempts to estimate the true flux of interstellar visitors, objects that reach peak brightness during periods when major observatories are affected by weather. Equipment failures or competing observational priorities may remain undetected despite satisfying all other detectability criteria. The concentration of the large telescopes in the Northern Hemisphere creates additional biases against objects whose peak visibility periods occur in southern sky regions, while the preference for dark, moonless observing conditions limits detection opportunities to roughly half of each lunar month. The development of space-based survey systems promises to eliminate many of these terrestrial observational biases while introducing new selection effects related to spacecraft capabilities and mission constraints. Space telescopes can operate continuously without weather limitations and achieve deeper limiting magnitudes than ground-based systems affected by atmospheric scattering and thermal backgrounds. Yet space missions also face constraints related to power consumption, data transmission rates, and pointing restrictions that may create different patterns of observational bias that must be carefully characterized to interpret detection statistics correctly. Future survey systems designed specifically for transient object detection will employ new observational strategies optimized for rapid motion targets with unpredictable arrival times and directions. Wide-field cameras with fast readout capabilities will monitor larger areas of sky with higher temporal cadence, while machine learning algorithms trained on synthetic interstellar object populations will identify candidates more efficiently than current pattern recognition systems designed for solar system objects. These technological improvements could increase detection rates by orders of magnitude, while extending the observable size range to smaller objects that currently remain below detection thresholds. The realization that current observations sample only the tip of the interstellar object iceberg transforms our understanding of galactic matter cycling and planetary system evolution. If theoretical predictions prove correct, the galaxy contains vastly more solid material in the form of unbound wanderers than remains gravitationally attached to stellar systems. This invisible population participates in the long-term chemical evolution of the galaxy through mechanisms that remain largely unexplored, carrying processed materials between stellar environments and potentially facilitating the exchange of organic compounds and even microbial life across interstellar distances that dwarf the scales accessible to any conceivable space exploration program. Chemical memory persists within these wandering fragments like ancient texts written in isotopic signatures and molecular structures, preserving records of stellar nucleosynthesis and planetary formation processes that occurred billions of years ago in galactic environments far removed from our own stellar neighborhood. Each interstellar visitor carries within its frozen interior a compressed library of information about the physical and chemical conditions that existed during its formation. From the temperature and pressure gradients in its parent protoplanetary disk, to the metallicity and heavy element abundances that characterize the interstellar medium when its birth stellar system first condensed from a collapsing molecular cloud. The isotopic ratios of light elements hydrogen, carbon, nitrogen, oxygen provide particularly sensitive records of formation environment conditions because these elements participate in temperature-dependent fractionation processes that operate differently under varying physical circumstances. The ratio of deuterium to ordinary hydrogen, for instance, reflects the thermal history of water ice formation in protoplanetary disks, with higher DH values indicating condensation at lower temperatures in the outer regions of stellar systems. Similarly, the abundance patterns of carbon and nitrogen isotopes preserve information about the degree of chemical processing that occurred in stellar atmospheres and interstellar chemistry networks before solid grains began to condense in cooling stellar winds. Presolar grains embedded within interstellar objects represent the most ancient components of their chemical inventory. Microscopic crystals that formed in the atmospheres of dying stars before the birth of the solar systems that eventually ejected these wanderers into interstellar space. These refractory particles, composed primarily of silicon carbide, diamond, and graphite, survived the violent processes of stellar system formation because their high melting temperatures and small sizes protected them from thermal destruction and gravitational settling. Their isotopic compositions provide direct snapshots of stellar nucleosynthesis processes, preserving the distinctive signatures of red giant stars, asymptotic giant branch stars, and supernova explosions that enrich the interstellar medium with heavy elements. The organic compound inventory locked within interstellar objects offers insights into the efficiency and complexity of prebiotic chemistry in environments beyond our solar system. Simple organic molecules methane, formaldehyde, hydrogen cyanide condense readily in the cold outer regions of protoplanetary disks and can subsequently undergo radiation-induced polymerization reactions during the interstellar journey to create more complex molecular structures. The preservation of these compounds in the near-absolute zero environment of interstellar space means that interstellar visitors could carry samples of organic chemistry that predate the formation of life on Earth, providing ground truth for theories about the cosmic distribution and evolution of biological precursor molecules. Mineral grain structures preserve records of the thermal and shock processing that occurred during planetary formation epochs, when these objects were still embedded within their birth stellar systems. The crystalline versus amorphous nature of silicate components reflects the peak temperatures experienced during formation, with crystalline phases indicating exposure to temperatures exceeding several hundred degrees Celsius through processes such as stellar wind heating, lightning discharges, or shock wave compression. Conversely, the presence of amorphous phases suggests formation in perpetually cold environments, where thermal processing remained minimal throughout the accretion and early evolution phases. The trace element abundance patterns in refractory components provide constraints on the stellar populations that contributed heavy elements to the interstellar medium from which these objects originally condensed. Different types of stars produce characteristic elemental abundance signatures through their nucleosynthesis processes and mass loss mechanisms. Massive stars synthesize large quantities of oxygen, silicon, and iron through hydrostatic burning phases and explosive nucleosynthesis during supernova events, while intermediate mass stars contribute enhanced carbon and nitrogen abundances through their asymptotic giant branch evolution. The specific patterns of trace element enrichment preserved in interstellar objects thus provide fossil records of the stellar populations that are active in their birth environments. Volatile compound ratios preserved in subsurface regions that escaped space, weathering during the interstellar journey offer additional clues about formation environment chemistry. The relative abundances of water, carbon monoxide, nitrogen, and noble gases depend on the temperature, structure, and chemical composition of the protoplanetary disk regions where these objects originally accreted. Objects that formed beyond the carbon monoxide snowline will preserve different volatile inventories than those that condense closer to their parent stars, while variations in the carbon-to-oxygen ratio of the original stellar system will affect the efficiency of organic compound synthesis and the stability of different molecular species. The magnetic properties of interstellar objects provide yet another window into their formation and evolutionary histories. Remnant magnetization acquired during condensation in the magnetized environment of a protoplanetary disk can survive for billions of years in materials with appropriate magnetic mineralogy, preserving records of ancient magnetic field strengths and orientations. Additionally, the interaction with galactic magnetic fields during the interstellar journey can induce new magnetic signatures that reflect the field configurations encountered during different phases of the objects wandering through space. Shock deformation features in crystalline materials record the violent dynamical events that launch these objects from their birth stellar systems into interstellar space. High-pressure mineral phases, planar deformation features, and shock-melted glass record the peak pressures and temperatures achieved during gravitational encounters with massive planets or tidal interactions with binary stellar systems. The preservation of these shock signatures provides direct evidence for the catastrophic nature of the ejection processes, while constraining the range of physical conditions that objects can survive during their transition from bound solar system members to free-floating interstellar wanderers. The stratigraphic layering that may exist within larger interstellar objects preserves chronological records of their accretionary histories and subsequent evolutionary processes. Objects that assembled gradually from smaller building blocks could preserve compositional gradients that reflect temporal variations in the chemistry and physical conditions of their formation environment. Similarly, the accumulation of interstellar dust and gas during their galactic wanderings could create surface layers that record the chemical evolution of the interstellar medium encountered during different epochs of their journey. Noble gas abundance patterns provide particularly robust traces of formation processes because these chemically inert elements resist alteration by most physical and chemical processes that occur during planetary formation and interstellar evolution. The relative abundances of helium, neon, argon, krypton, and xenon isotopes preserve signatures of stellar wind implantation, cosmic ray spallation, and radioactive decay processes that operated in the object's formation environments. These patterns can distinguish between materials that formed in different stellar systems and potentially identify objects that originated in stellar environments with unusual chemical compositions or evolutionary histories. The preservation fidelity of these chemical records depends critically on the thermal and radiation processing that occurred during both the formation epoch and the subsequent interstellar journey. Materials buried beneath several meters of overlying material remain largely protected from cosmic ray bombardment and retain their original chemical signatures with minimal alteration. Surface layers, however, undergo continuous modification through space weathering processes that can obscure or destroy the original chemical information while creating new molecular structures that record the environmental conditions encountered during interstellar travel. Future analytical techniques applied to samples returned from interstellar objects could decode these chemical archives with unprecedented precision, revealing details about stellar nucleosynthesis, planetary formation, and galactic chemical evolution that remain inaccessible through any other observational approach. Ion microprobe analysis of individual mineral grains could measure isotopic ratios at the parts per million level, while advanced mass spectrometry techniques could identify complex organic molecules and characterize their stereochemical properties. These measurements would provide the first direct sampling of matter from other stellar systems, offering ground truth for theoretical models of cosmic chemical evolution that currently rely entirely on remote observations of distant astronomical objects. The implications of accessing such detailed chemical records extend far beyond the specific scientific questions related to planetary formation and stellar evolution. These archives preserve information about the galactic environment that existed billions of years ago, when the universe was younger and stellar populations had different characteristics than those observed today. The chemical signatures locked within interstellar visitors thus provide unique windows into cosmic history that complement and extend the archaeological records preserved in meteorites and terrestrial rocks from our own solar system's formation epoch. Galactic archaeology emerges from the study of these silent messengers, transforming our understanding of cosmic evolution through the physical examination of matter that has travelled vast distances across both space and time. Each interstellar visitor functions as a natural space probe that has sampled conditions in distant stellar environments and carried those samples across hundreds of light years to deliver them directly into our astronomical laboratories. The information encoded within their chemical compositions and physical structures provides unprecedented access to the properties of stellar systems that will forever remain beyond the reach of human space exploration. While their isotopic signatures preserve records of galactic chemical evolution that span billions of years of cosmic history, the concept of using small bodies as archaeological artifacts represents a fundamental shift in how astronomers approach the study of galactic evolution. Traditional methods rely on remote observations of distant objects, stellar spectra, planetary atmospheres, protoplanetary disk emissions that provide information about current conditions but offer limited insights into historical processes. Interstellar visitors, by contrast, carry physical samples that can be analyzed with the full arsenal of laboratory techniques developed for meteorite and planetary science research. Mass spectrometry, electron microscopy, X-ray crystallography, and ion probe analysis can reveal details about formation processes, thermal histories, and chemical evolution that would be impossible to extract from remote observations alone. The temporal dimension of galactic archaeology becomes particularly significant when considering the ages of interstellar objects and the timescales associated with their journeys through space. Objects ejected from stellar systems during the galaxy's youth preserve chemical signatures that reflect conditions existing when the universe was significantly younger, and stellar populations had different characteristics than those observed today. The earliest generations of stars contained lower abundances of heavy elements, different ratios of various isotopic species, and distinct patterns of chemical enrichment that evolved over billions of years through successive episodes of star formation, stellar evolution, and supernova nucleosynthesis. The spatial dimension adds another layer of complexity to galactic archaeological investigations. Interstellar visitors originate from stellar systems distributed throughout the galaxy's disk, and potentially even from other galactic components such as the thick disk, stellar halo, or globular cluster populations. Each galactic environment is characterized by distinct chemical signatures that reflect its star formation history, stellar mass distribution, and degree of chemical mixing with surrounding regions. Objects that formed in the inner galaxy, where stellar densities are high and supernova rates are elevated, will preserve different isotopic patterns than those that condensed in the outer disk regions, where heavy element abundances remain lower and chemical evolution proceeds more slowly. The preservation of chemical information during interstellar transport depends on the physical processes that affect solid materials during their million-year journeys through the galactic medium. Cosmic ray bombardment gradually alters surface compositions through nuclear spallation reactions that create new isotopic species while destroying others. But these modifications typically penetrate only the uppermost few meters of material. Subsurface regions remain largely unaffected by space-weathering processes, preserving pristine records of formation environment chemistry that can be accessed through drilling or impact excavation of protective surface layers. The detection of isotopic anomalies in interstellar objects would provide direct evidence for stellar nucleosynthesis processes operating under conditions different from those that characterized our own solar system's formation. Unusual ratios of oxygen isotopes could indicate formation in environments enriched by specific types of supernovae, while anomalous silicon or iron abundances might reflect contributions from stellar populations with different mass distributions or metallicities. Such discoveries would constrain models of galactic chemical evolution while providing the first direct samples of matter processed in alien stellar environments. The organic chemistry preserved within interstellar objects offers insights into the cosmic distribution and evolution of prebiotic molecules that could eventually lead to the emergence of biological systems. The detection of amino acids, nucleotide bases, or other complex organic compounds would demonstrate that the chemical precursors of life can form and survive in environments beyond our solar system. More sophisticated analyses could reveal whether such molecules exhibit the chirality patterns associated with biological processes or remain in the racemic mixtures expected from abiotic synthesis pathways. The mineral assemblages found in interstellar visitors provide information about the pressure and temperature conditions that existed during their formation in protoplanetary disks around other stars. High-pressure phases indicate exposure to shock processing during planetary formation or ejection events, while the presence of hydrated minerals suggests interaction with liquid water in environments where temperatures periodically exceeded the freezing point. These mineralogical records complement the chemical information by revealing the physical processes that shaped solid materials during their formation and early evolution. The magnetic properties of interstellar objects preserve additional archaeological information about the magnetic field environments that existed in their birth stellar systems. Remnant magnetization acquired during condensation in magnetized protoplanetary disks can survive for billions of years, providing direct measurements of ancient magnetic field strengths that can be compared with theoretical models of early stellar system evolution. The orientation of magnetic vectors relative to object structure could even preserve information about the geometry of ancient magnetic fields and the dynamics of protoplanetary disk accretion processes. Comparative studies of multiple interstellar visitors will eventually reveal the degree of chemical diversity that characterizes stellar systems throughout the galaxy. Objects that show similar isotopic patterns might originate from the same galactic region or stellar population, while those with distinctly different compositions could represent samples from environments with fundamentally different formation histories. Statistical analysis of large samples could identify correlations between chemical signatures and estimated ages or trajectories that would constrain models of galactic structure and evolution. The potential for discovering truly exotic materials in interstellar objects adds an element of unpredictability to galactic archaeological investigations. Objects that formed around unusual stellar types carbon stars, Wolf-Rayet stars, or neutron star companions might contain mineral phases or isotopic signatures unknown in our solar system. Similarly, materials that experience processing in environments exposed to intense radiation fields or unusual chemical conditions could preserve records of physical processes that have no terrestrial or solar system analogues. The technological challenges associated with detailed analysis of interstellar object samples will require the development of new analytical techniques optimized for small sample sizes and potentially hazardous materials. Remote robotic analysis systems might be necessary for initial characterization of samples that could contain exotic isotopes or unknown chemical compounds. Advanced containment and handling procedures would ensure that the scientific value of returned samples is preserved while protecting terrestrial laboratories from potential contamination by alien materials. The integration of galactic archaeological data with observations of contemporary stellar systems will create a comprehensive picture of cosmic chemical evolution that spans the entire history of the galaxy. By comparing the properties of ancient materials preserved in interstellar visitors with the compositions observed in young stellar systems today, astronomers can trace the efficiency of chemical mixing processes and identify the timescales over which galactic chemical gradients develop and evolve. This temporal perspective on galactic chemistry represents one of the most significant potential contributions of interstellar object research to our understanding of cosmic evolution. The broader implications of galactic archaeology extend beyond purely scientific questions to fundamental issues about the cosmic context of life and intelligence. If interstellar objects preserve evidence for complex organic chemistry, or even fossilize microbial life from other stellar systems, they would demonstrate that the chemical foundations of biology operate throughout the galaxy. Such discoveries would transform our understanding of life's cosmic significance, while providing the first direct evidence for biological processes operating beyond our solar system's boundaries. Future encounters await discovery in the vast darkness that surrounds our solar system. Invisible wanderers following trajectories that will eventually carry them through our detection zone during the coming decades and centuries. Statistical models derived from the handful of confirmed interstellar visitors predict a steady stream of similar objects approaching from random directions throughout the galaxy. Their arrival times unpredictable, but their eventual detection almost certain as astronomical survey capabilities continue to expand and improve. The next generation of wide-field telescopes will monitor larger areas of sky with greater sensitivity, detecting smaller and more distant objects, while providing longer lead times for detailed observational campaigns that could revolutionize our understanding of the interstellar object population. The Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, represents the most ambitious attempt yet undertaken to catalogue the transient astronomical phenomena that populate our cosmic neighbourhood. This revolutionary facility will photograph the entire southern sky every few nights for 10 years, creating an unprecedented database of moving objects that will capture interstellar visitors from the moment they become detectable until they fade beyond the reach of ground-based observations. Computer models predict that this survey alone could discover dozens of interstellar objects each year, providing the statistical samples necessary to characterize population properties and identify rare or unusual specimens that might preserve unique records of galactic chemical evolution. Space-based infrared telescopes promise to extend the detection range for interstellar visitors by observing their thermal emission rather than relying entirely on reflected sunlight. Objects too dark or too distant to appear in visible light surveys become detectable in infrared wavelengths, where they glow with heat absorbed from solar radiation or residual warmth from radioactive decay processes. The James Webb Space Telescope and future infrared observatories could identify interstellar objects months or years before they reach peak brightness, providing extended observational opportunities that would allow detailed spectroscopic characterization of pristine surfaces before solar heating begins to drive cometary activity or alter surface chemistry. The development of rapid response observational capabilities will maximize the scientific return from future interstellar visitor discoveries. Traditional astronomical scheduling processes, with their months-long proposal review cycles and predetermined observing programs, cannot accommodate targets that remain visible for only a few weeks. Instead, major observatories are implementing automated alert systems and pre-approved target lists that allow high-priority observations to begin within hours of object identification. These systems bridge the gap between discovery and detailed characterization, ensuring that critical measurements can be obtained before visitors disappear back into the cosmic deep. Robotic space missions to intercept interstellar objects represent the ultimate goal of this emerging field, though the technical challenges remain formidable. The high velocities of hyperbolic trajectories require massive energy expenditures to achieve rendezvous or even close flyby geometries, while the unpredictable arrival times make it difficult to prepare missions in advance. Conceptual studies have explored various mission architectures, from high-velocity flyby spacecraft to solar sail-powered interceptors that could gradually match velocities with slowly moving targets. Future missions might employ nuclear propulsion systems or ion drives to achieve the large velocity changes necessary for interstellar object rendezvous. The scientific payoff from such missions would be transformational, providing close-up images of alien worlds and direct compositional measurements that cannot be obtained through remote observations. Landing missions could return samples to Earth for detailed laboratory analysis, while orbiting spacecraft could monitor outgassing processes and map surface compositions with unprecedented spatial resolution. The discovery of organic compounds, unusual mineral phases, or isotopic anomalies would constrain models of stellar system formation, while potentially revealing evidence for biological processes operating beyond our solar system. Artificial intelligence and machine learning algorithms will play increasingly important roles in identifying and characterizing interstellar visitors as detection rates increase beyond human capacity for manual analysis. Neural networks trained on synthetic populations of interstellar objects can learn to recognize the subtle, dynamical signatures that distinguish true interstellar visitors from solar system objects with unusual orbits. Advanced pattern recognition systems could identify spectroscopic features associated with specific formation environments, or detect rare compositional signatures that might otherwise be overlooked in routine survey data. The integration of multiple observational data sets will provide comprehensive characterizations of individual objects that exceed the information content obtainable from any single measurement technique. Combining photometric, spectroscopic, astrometric, and polarimetric observations creates multidimensional portraits of visitor properties that constrain physical models and formation scenarios. Future data fusion algorithms could automatically cross-correlate observations from different telescopes and wavelength ranges, identifying subtle correlations and anomalies that reveal previously unrecognized aspects of interstellar object physics. International cooperation will become essential as the field of interstellar object research expands beyond the capabilities of individual nations or institutions. The brief observational windows and global distribution of major telescopes require coordinated campaigns that maximize coverage while minimizing duplication of effort. Standardized data formats and analysis protocols will facilitate rapid sharing of observations between research groups, while international funding mechanisms could support dedicated missions to particularly interesting targets that exceed the resources available to single space agencies. The democratization of astronomical observations through advanced amateur equipment and citizen science programs could contribute significantly to interstellar object discovery and monitoring. Modern CCD cameras and computerized telescopes place detection capabilities within reach of dedicated amateur astronomers, while crowdsourced data analysis projects could harness collective human intelligence to identify candidates in vast survey datasets. The next Oumuamua or Tuai Borisov might be discovered by an amateur astronomer using equipment that would have been considered professional grade just a few decades ago. Educational and public outreach opportunities surrounding interstellar visitor discoveries provide unique contexts for engaging broader audiences with current astronomical research. These objects capture public imagination because they represent tangible connections to other worlds. Physical ambassadors from stellar systems that will forever remain beyond human reach. Interactive visualizations, real-time tracking websites, and educational programs built around interstellar object discoveries could inspire new generations of scientists while demonstrating the relevance of astronomical research to fundamental questions about our place in the universe. The long-term vision for interstellar object research extends toward comprehensive surveys that catalogue thousands of visitors and provide statistical insights into galactic populations that remain invisible through any other observational approach. Such surveys would reveal the efficiency of planetary formation processes around different types of stars, constrain models of stellar system evolution, and provide direct samples of matter from throughout the galaxy's star-forming regions. The accumulation of large statistical samples would enable demographic studies that correlate object properties with estimated ages, trajectories, and source populations. Future technological developments in propulsion, robotics, and analytical instrumentation could eventually enable routine interception and sample return missions that transform interstellar visitors from astronomical curiosities into regular sources of extraterrestrial material for laboratory analysis. Automated mining spacecraft might rendezvous with particularly large visitors to extract core samples for return to Earth, while swarms of smaller probes could monitor multiple objects simultaneously to characterize population properties through in situ measurements. Such capabilities would establish interstellar object research as a cornerstone of comparative planetology and galactic archaeology. The recognition that we inhabit a galaxy filled with wandering fragments of other worlds fundamentally changes our perspective on cosmic isolation and connectivity. These silent messengers demonstrate that stellar systems throughout the galaxy exchange matter through processes that operate over millions of years, creating networks of chemical and potentially biological interaction that span distances incomprehensible to human experience. Future encounters with these cosmic time capsules will continue to reveal the hidden connections that link our solar system to the broader galactic community of worlds. Cosmic loneliness settles like stardust across the vast emptiness between stellar systems, where these ancient wanderers continue their silent journeys through the galactic night. In the profound darkness that separates one star from another, Oumuamua tumbles onward at 26 kilometers per second, its reddish surface slowly cooling as it recedes from the warmth of our sun toward temperatures that approach absolute zero. Borisov follows its own trajectory through different regions of space, its nucleus still shedding wisps of sublimating ice that catch starlight and scatter it into the cosmic void like breath, visible on a winter morning that extends across light years. Both visitors now travel beyond the orbit of Saturn, their reflected sunlight too faint for even the most powerful telescopes to detect against the stellar background. Yet they persist in their ancient purpose, carrying within their frozen interiors the chemical signatures of worlds that formed when the galaxy was young, preserving isotopic ratios and molecular structures that record the nucleosynthesis processes operating in stellar furnaces that burned out billions of years before Earth's continents took their current shapes. Their journey toward the edge of the solar system marks not an ending, but a return to the patient voyage that has already carried them across hundreds of light years and will continue for millions of years more. The darkness they enter contains no landmarks, no signposts to mark their progress through the interstellar medium. They navigate by no compass except the gravitational gradient of the galaxy itself, following trajectories that curve gently through space-time under the collective influence of 400 billion stars. Their paths will carry them past other stellar systems, perhaps close enough for alien astronomers to detect their passage and wonder, as we have wondered, about the distant worlds that gave them birth. The questions they raise will outlive the civilizations that ask them, echoing through cosmic time like light from distant stars. In this vast ocean of space and time, where distance and duration merge into a single measure of separation, these messengers from other suns continue the slow circulation of matter that connects every stellar system in the galaxy. They remind us that we are not inhabitants of an isolated island, but citizens of a universe where every world exchanges pieces of itself with every other world, where the boundary between home and abroad dissolves into the gentle drift of cosmic evolution. Their silence contains all the stories that matter, written in the patient language of atoms and isotopes that requires no translation across the light years. Sleep comes easily in such vastness, where time moves at the pace of stellar evolution and change occurs on scales that dwarf human worry. The cosmic perspective offers its own form of peace. The recognition that our brief moment of awareness participates in processes that began before the sun was born and will continue long after the last star has exhausted its nuclear fuel. In this context, the day's anxieties fade like morning mist before the sun, replaced by the deeper rhythm of galactic rotation and the slow breath of stellar birth and death that marks the passage of cosmic seasons. The interstellar visitors carry this message of temporal perspective as they fade into the night, their brief passage through our neighborhood serving as a reminder that we too are temporary arrangements of matter and energy, privileged to witness for a moment the vast patterns that govern the universe. Their journey continues in darkness, punctuated only by the distant light of stars, a meditation on persistence and patience that needs no conscious awareness to achieve its purpose. They have become one with the cosmic silence, travelling forever toward horizons that recede at the speed of light.